So we're now in the Maria Luisa Park. The park is 100 acres big and it's filled with trees, flowers, benches, all kinds of structures, fountains, water, and also vases, which really give it a very nice feel. It's a beautiful place on a day like this to walk around and enjoy nature. On the southern side of the park is a collection of buildings, and these are museums. And my personal favorite museum is the Archaeological Museum, which you can also visit there. I've already been there many times, and I plan to go there a couple of times more.
So these gardens were used to belong to the Infanta Luisa Fernanda, and it's hard to believe that these huge gardens could belong to one single person. But the positive thing is that in 1893, she decided to donate them to the city of Seville. And now it's open to the public, so anyone can come here and enjoy with family, with friends, and have a lovely day. Now I give you the word.
Thank you, Adela. It was it's really a pity that we are not there enjoying Sevilla. Yeah. Okay. So, yeah, I think they can also see the videos later on, right? So anyway, let's start with the session. As I told you before, this is the session about conformance and prediction, and we have 4 very interesting papers. Three of them are on prediction, and in particular look at predictive process monitoring from different perspectives. And the fourth one is on conformance. So I think I can leave the floor to the first speaker, but before doing that, I would like to remember you that you can ask questions either by using the Q&A feature in Zoom or raising your hand in Zoom, and then we will either read your questions or we are going to allow you to ask your questions by yourself. So I think that Farbod, you can go. The first paper is a paper about predictive process monitoring, and in particular the title is Predictive Business Process Monitoring via Generative Adversarial Nets, the Case of Next Event Prediction. And it is authored by Farbod, Maimori, Marcello La Rosa, Sara Erfani, Zara Dasht-Bogorgi, and Ilya Verenic. If you can share the screen, Farbod. With your presentation. I cannot see it.
Can you see my screen now?
Yes, yeah, I can, yeah.
How about now?
Yes.
Okay.
Please.
Can I start?
Yes, sure.
Hello, everyone, and welcome to this short presentation titled Predictive Business Process Monitoring via Generative Adversarial Net, the case of next event prediction. As an introduction, as you can see, predictive business process monitoring is an area of process monitoring that is concerned with predicting future characteristics of an ongoing process case. In general, so existing tasks can be divided into 3 categories: next activity and timestamp prediction, the outcome and remaining time prediction, suffix prediction. And so I'm not defined these categories because I think that everybody knows. In this presentation, we focus on the first task, which is the next activity and timestamp prediction. So let's present the first task in a more formal way to see what we need to compute. If we present an ongoing process execution by x1, x2, and xt, where xi shows an event and its attributes such as event's label and its timestamp, the first task boils down to learning conditional probabilities at different timestamps. In short, given x1 to xt, we are looking for x at t plus 1 that maximize the following conditional probability. This formula PD is the underlying distribution that we want to approximate using the event log, using the data recorded in the event log. And it is the main question that we are going to address in this presentation. So let's talk about the background a little bit. So before getting into the details, so I'm explaining a little bit about the different machine learning models. Discriminative models from probabilistic perspective, machine learning models can be categorized into two classes, so according to their learning mechanism. So discriminative models such as logistic regression learns a conditional probability distribution, whereas generative models such as naive-Bayes learn a joint probability distribution. In other words, this approach learns different concepts. The former learns a decision boundary, as you can see from the picture, in the input feature space, whereas the latter learns a very complicated hyperplane in the input feature space. So discriminative models are used for supervised learning tasks, whereas generative models can be used for both supervised and unsupervised learning tasks. And last but not least, I can tell you that the generative models are much more challenging to compute. So because we are dealing with sequential data, we use a special sort of neural network, in a sort of architecture called long short-term memory, LSTM. And the details of this architecture is presented in the paper, so I'm not going through it. So interested readers are welcome to read the paper. And but more importantly, so this paper, I'm going to explain a little bit about that GANs, or generative adversarial net. A GAN architecture is a framework that allows a neural network to be trained in a generative way. A GAN architecture has two components, so the generator and the discriminator. Each can be any kind of a neural network, such as LSTM, CNN, or fully connected neural network. But how does it work? In such network, we consider two sets of data sets. First, real example, which are ground truths, and the second, fake examples, which are the output of the generator. The generator task is to learn the probability distribution that generates a real example. In the context of process modeling, traces of input in log can be regarded as a real example. In this framework, the generator is fed by a random number, and its task is to generate some sequences, which are fake example. The quality of such an example must be enough good to confuse the another network, i.e. discriminator, and distinguishing them from real example. The generator improves its output by receiving feedback from the discriminator. So we didn't represent it in this picture for the sake of simplicity. Just the two networks can start an adversarial game in which each player wants to maximize its outcome at the cost of minimizing the other's outcome. At the end, the generator might be able to generate sequences that are very close to the real example. In this work, we present the following, we adopt the following data representation. We represent categorical variable using one-hot vector encoding, which is a 0-1 representation for categorical variables. And also we augmented it with the timestamp, which is the time elapsed between the timestamp on one event and the event's timestamp that happened one step before. So the details are in the paper, and interested readers are welcome to look at it. The related work, so several works address different predictive process monitoring tasks. However, because we are in this work, we focus on deep learning model, so we list the related work regarding the predictive process monitoring tasks. As you can see, most of the available works are based on LSTM architecture, and recently CNN, or convolutional neural network, show a competitive performance. It must be mentioned that all these works, or let's say previous works, are discriminated, i.e. they learn a decision boundary in the features. But the main question you might ask is, what is the advantage of a generative model over a discriminative model? Well, in this slide, so we give you a motivational example. Assume that we have the following data set, which we highlighted two existing groups. The discriminative model learns a boundary that separates two classes. However, depending on the parameters of the model, these boundaries could have different shape, as you can see at the bottom of the slide. So discriminative models will generalize differently on instances according to their performance. However, a generative model learns a joint probability distribution, i.e. the way the examples that can be generated. Therefore, it might better generalize on unseen example and for a prediction test. However, it is very expensive to compute such a joint probability distribution. In this work, so this is the proposed framework. It is inspired by adversarial net, and we two LSTM neural network against each other. So the generator versus the discriminator. In general, given a prefix, the generator's task is to predict the next event's attribute, whereas the discriminator's task is to discriminate whether it is a fake example or real example. This is an adversarial game between two networks. The generator maximizes performance by receiving feedback from the discriminator. So you can see the arrow number 3 in the figure. And the discriminator updates its weight by getting prediction from the generator and the ground truth. So in the picture, arrow number 1 and number 2. Well, in more details, the adversarial predictive process monitoring in this presentation works as follows. So given a prefix and its ground truth, we create a real and fake example as follows. On the one hand, we concatenate the last prediction to the input prefix and call it the fake prefix. And on the other hand, we concatenate the last element of corresponding ground truth to the input prefix and call it a real prefix. Also, we fit with random numbers the initial hidden state of the generator. However, for the sake of simplicity, so we didn't mention it here. The min-max game, as we defined, I explained informal in the previous slide, is formally presented here. The discriminator maximizes the above formula by assigning xk, which is a real example, to the real prefix, and assign zk, which is a fake example, to the, let's say, fake class. At the same time, the generator minimizes the above formula by generating fake prefix such that the discriminator assign it to real prefix. This is a min-max game, and this above optimization problem finishes when the Nash equilibrium happens. It is a point in the optimization search space where neither the generator nor the discriminator can improve their objective functions. Reaching this point is very difficult in practice, and hence optimizing GAN or min-max game is very challenging. It's an open research avenue. Another important issue during such optimization is called a mode collapse, which the generator learns to produce only one kind of event. In other words, so the generator fools the discriminator only by a single output. Given the min-max optimization in the previous slide, the training procedure of the proposed approach is as follows. For each input prefix, we compute we create the corresponding fake and real prefixes. Next, we update the parameters of the generator and discriminator accordingly, and according to the min-max gain. And it must be mentioned that we update the parameter of the generator using a maximum likelihood estimation, so like a traditional training way. So this way, alleviate the effect of mode collapse a lot in our experiment. In detailed analysis of this, the detailed analysis of this algorithm is provided in this paper, and interested users are welcome to read it. And for the experiment, this approach is implemented in Python 3.7. We evaluate our approach over 4 real data set. As you can see, the statistics, the baseline is selected according to the tools availability and then the performance. And we use the temporal splitting 80-20 for training and testing. To measure the performance of our framework against baseline, we use accuracy and MAE. So however, the accuracy is not a good metric to measure the prediction task. However, it was adopted to be compatible with the baselines. The complete details of experimental setup is provided in the paper. So this slide shows the result of this presentation. First, the top right table shows, this table shows that the average accuracy and MAE for different data set and baselines. For the accuracy, one can see that the proposed approach outperforms the baseline, so you can see the first line. However, for the weighted MAE, we presented approach, the presented approach is superior in all data set except for BPI 2017. And another obvious pattern, as see the gray line, is the stability of the proposed approach against baseline as the prefix gets longer. So there is no fluctuation. This behavior can be attributed to the different learning mechanisms, such as min-max gain, that allow the model to learn a ground truth distribution. Finally, we observed 3 patterns between the players when we optimized the min-max gain. The generator and the discriminator during we followed 3 patterns, as you can see from in this slide, when we maximize the min-max gain. On the one hand, the min-max gain cannot be converged, as one can see in figure A. Obviously, in this case, no benefits can be obtained from the min-max gain. On the other hand, the convergence can happen very early to late, as demonstrated in figure B and C. So these are the points that Nash equilibrium happened. So we see several opportunities, but in general, the 2 main feature avenues are First, we can adopt the purpose approach with a little bit modification to other process mining tasks, such as stochastic conformance checking or probabilistic process discovery, or any task that might need to estimate a probability distribution. On the other hand, one can explore other unsupervised learning models or architecture for estimating probability distributions. That can be used also for other process mining tasks. And thank you very much for your attention.
Thank you, Parbod, for the presentation. You were also in perfect time.
So we have a question in the Q&A, and we have a question by Ingo in the audience. I'll start by reading the Q&A question, perhaps, and then Ingo will go next. So there's a question from an anonymous attendee. I have two questions concerning training your GAN. As GANs are notoriously hard to train due to the fact they are highly unstable and require a lot of hyperparameter tuning, GANs are very prone to under and overfitting. My question is, have you used train validation test data split to ensure that after you trained your model on the training set and tuned your GAN network on the validation set, you can evaluate the learned models on the test data set? That's the first question.
That's a good question. The thing is that, yes, the training GAN is quite difficult, and it would be even much more difficult even working with the discrete elements. And we didn't use any, indeed, so the GANs, the training finishes when Nash equilibrium happens. But in our experiments, we didn't reach this point in all of our experiments. So we stopped, as you can see from the paper, we stopped training at the threshold. So yes, that's correct. So the optimization is difficult.
Thank you. Then there's a follow-up by the same attendee. As you have demonstrated in your presentation, your GAN model achieves impressive results. In some cases, over 30% improvement over traditional methods, which results in an accuracy close to 95%. Where do you perceive the main improvement may come from?
Well, this is a very, very good question. So this is the thing that many researchers ask. So when working with GAN, because actually what we proposed here is an adversarial training, is not a generative model in a pure way. And because as I said, so we train the model with our training procedure has two parts. One is the training you're using traditional method like MLE, and the other one is the optimization with the min-max game. So this is the future work that we are going to explore it. Okay, this improvement so can be attributed to which part? Is it only for the min-max game, or it's the collaboration, I don't know, between these two optimization? So yes, this is the thing that needs to be explored in the future work. Thank you for the question.
Thank you. Ingo, you're next.
Yes, thanks for both, and Arik. So I have a quick question and a follow-up question. The first question is, do you train on the basis of prefixes? So, for example, do you look at prefixes of the length 2 and train your model based on that?
Yeah, we consider different prefixes, trained for each prefixes. Separately.
Okay, then my follow-up question is, have you looked at our case forum paper from 2018, Chris Klinkmüller being the first author? Because there we basically show that doing so results in a problem. Essentially, you are changing the distributions from which you're learning by cutting the trace into prefixes of different length. So if you're training on the basis of prefixes, then you are quite likely to have a model that results in unjustified predictions.
What is the question? Oh, sorry, I didn't understand. Could you?
The question was, have you looked at this paper? Are you familiar with this result?
Oh no, I haven't looked at that paper, but I'm going to look at it.
Yes, that would seem very useful, because in there we include like synthetic data sets which you can use to essentially test your approach and see whether your approach is immune to that.
Sure, I will take a look at it. Thank you.
Thanks, Ingo. Chiara, do we have time for one more question?
One more question, yeah.
So Yari is asking in the Q&A, do you already have an idea how you could use this GAN model for discovery? How could you map the LSTM of the generator to a readable process model?
Well, GAN is a framework, and it's the more matter of art than science. No? You should propose a game between two players. And then maybe you can start with a basic model, and then, I don't know, you can define some metric for your process model like fitness, precision, and these two networks can fight each other against these two and these metrics until they reach a convergence. Well, this the thing that we proposed here, so it works with sequential data, but I can tell you the original GAN it is proposed for continuous value data such as images. So it needs lots of consideration when you work with discrete value data.
Thank you.
Thank you again.
Yeah,
I think
I don't see further questions in the Q&A nor in the...
No, I think there is a bit of discussion going ahead, but if you have other questions, maybe you can use the copy with authors for discussing this. Okay. So I think we can move to the next presentation.
Thank you very much.
Thank you, Farbod, and thank you all for the questions. I think we can move to the next presentation, and I think Renuka is presenting it. Can you share your screen, Renuka? So
yes, sure.
The paper is exploring interpretable predictive models for business processes, and it is authored by Renuka, Singatta, Caterina Moreira, Chuno Yang, and Alistair Barros. So, Renuka, the floor is yours.
Yeah, thank you, Chiara. So this is the joint work with Katrina, Chun, and Alistair from Queensland University of Technology. So as Farbod also mentioned, the primary approach to building predictive models is you take an event log, you look at historical past executions, and then we train a machine learning model. And these could be different approaches that we could use. And finally, if given a partially executing case, the objective is to come up with a prediction. And this prediction could be different things. You could either predict next event, completion time, suffix, anything, pretty much the outcome, the resource who needs to execute, depending on the problem that we want to solve. There could be different outcomes that we want to predict. So what exactly is the problem here? The problem is that in most of these approaches, we are using some machine learning model or a deep learning model as a black box. We really don't know what's the internal mechanisms that are leading to the prediction. So different questions could arise. Why did the model work? Can I trust these results? Or is there a bias or an error? So unlike you would say a software program, debugging a machine learning model is quite difficult. You wouldn't know if your data is not representative of the actual reality. Things could go wrong. So there are a lot of reasons why we would want to understand why a prediction is made. And there have been many studies which highlight this scenario that a model could make a right prediction, but the reasoning could be incorrect. So this is one of the work where the machine learning model was making the right prediction in the healthcare domain, but was using some additional information about how a metal plate was kept while taking these X-rays on different patients. And then you also have this quite a famous work on explaining black box models, where the model was predicting not whether it was a husky or a wolf, not by using the information about the features of the animal, but by looking at patterns like whether there was a snow or not snow. And this could be because of the bias in the data. And often, so the biggest challenge is there is this trade-off between accuracy and interpretability. So if you would look at the literature around, there are simple models like the additive linear regression models or decision trees, which have high algorithmic transparency. So they are interpretable, but often their accuracy is low. Again, this is just an observation that it's often low, not always. Whereas if you look at a complex model like the deep learning models, we have very low algorithmic transparency, and they often have high accuracy. But ideally, we would want both. We would want accuracy and interpretability. And it's not that explainability has been, it's been a focus for a very long time, but it's gaining importance because of new regulations which are mandating automated decision systems to give some reasoning behind the decision making. Now, to generate explanations, there are two widely used approaches. One is post hoc. So here you still use a black box model, and then you explain the model later. So the most widely used techniques are LIME and SHAP. And so what they do is they approximate the black box model locally around a data point. And the approximate model has to be a linear model to bring in that transparency. Now, there have been concerns here by many people about the fact that it is still an approximate model, one, and two, we really don't know if it is actually giving the same explanation as what the complex model is using. So that's the challenge. The other option is, can we build a model that is not black box? Can we build a model which can explain itself? So that's an interpretable model. So in the context, I mean, the scope that we are looking at is the existing deep learning models. There have been quite a lot of work in the recent past where different LSTM architectures have been used to make a prediction. And there are various things that are predicted. Either it's the next activity, remaining time, suffix, and so on. Most of the models have focused on accuracy. And what we wanted to look at is see if we could meet some of these benchmarks of accuracy, but bring in interpretability. And so as in the previous presentation you saw, LSTM, long short-term memory, is largely used for making predictions in business process, simply because it's a sequence prediction problem. So given a case, you could extract various features, like you could extract the activity sequence, the resource roles that have been done. And this is largely based on the work done by Carmago, where these were the things that were used: the resource, the next activity, and the time difference between the last event. Then there are model architectures, different types of model architectures that were evaluated. So what we wanted to look at is this is again another very seminal work that is used by Badano, largely in the context of natural language processing. So there also you would say, given the sequence of words, can we actually soft search and find out which parts of the sentence are leading to a prediction? So they are the most relevant information is there. So if you map it to business process, we would say, can we focus on the set of events that influence a prediction of the next event? But in the context of our architecture, we would need a dual attention, because one, a case has multiple events and each event has multiple attributes. So we want to know both. We want to use attention mechanism to not only look at which events influence the prediction, but we also want to look at which attributes of an event influence prediction. And even dual attention is gaining a lot of focus. So there's been this work in the context of healthcare domain where dual attention models were used to predict whether a patient is at risk or not. So we defined various architectures. The first thing is you look at the activity, the role, and the time since the last event. You have, so here we have both categorical and numeric attributes. So for the numeric attributes, we don't do anything, but for categorical attributes, we use the binary vector representation and we use an embedding layer. But I'll just come to how we don't change any dimension size of the embedding layer. And then we actually use a bi-LSTM. And then we build an attention around which event influences the prediction. So that is attention on an event. The other next architecture is, can we look at attention on the event as well as attention on the attributes of an event? So that's where you have two bi-LSTMs, and then you have a softmax and a tanh, and then you build the context vector. And the third one was, we were looking at, can this architecture not only predict next event, can it also predict the remaining time? So there were a few things that had to be done for model interpretability. So one is to make sure that we don't reduce the embedding size, because that's when the information is lost. So the embedding layer is largely to convert the binary vector into a numeric, but there's no dimensionality reduction. Then we have the attention slightly different. So here we don't look at the output of the bi-LSTM layer, but we actually take directly the input. So again, there's a clear information of the input right from the beginning till the context vector is computed. So to actually evaluate our approach, we had to look at two things, saying, can we evaluate the accuracy as well as the interpretability? How do we know it's giving the right explanations? So here we looked at the logs that have been used in previous studies. So these are all the logs that we looked at, and they vary based on number of activities, the mean length of a trace, and so on. So in our experimental approach to evaluate these models, what we do is, you would see the first few steps are very standard in evaluating any machine learning model. So you take the event log, you split it into train and test. We have the training with the cross-validation to tune the hyperparameters. And then we test the model on the remaining test data. That's the standard approach. What we also looked at is we generated explanations on the test data. And then we looked at, can we verify if these explanations are indeed right using an ablation study. So here's an example. So the paper has a lot more details, but here I'll just pick up two examples. So here we looked at, for example, these different logs with different sequence lengths or prefix lengths. Right. So we have helpdesk, which is only 5, because the helpdesk is, each trace is of a smaller length. Whereas for BPIC 2012, we looked at the prefix lengths of 5, 10, and 15. And then we evaluated the accuracy and generated the attention, the event attention. So here you would see that for helpdesk, the attention weights are highest on the last activity. The last two activities are enough. In fact, there's 80% attention weight only on the last activity. Whereas if you look at BPIC 2012, you would see that the attention weights are at least on the last 5 activities. So to evaluate whether this is indeed true, what we did is we trained the model with shorter prefix lengths. So all the models were trained and evaluated for accuracy with just 2 prefixes. 2 events. And here you would see, if you look at helpdesk, the accuracy really doesn't reduce, simply because it's only using the last event's information for the prediction. Whereas if you see BPIC 2012, the accuracy reduces. And so that's one way of saying that these explanations were indeed reflecting what the model is using for the prediction. The next step was looking...
2 minutes.
Yeah, okay. Sure. The next step was on looking at the attributes as well. So that's where we extracted the information. And here I have the example of BPIC 2012. So here the only the absolute value matters. And so what we did is we looked at all the attributes. We then removed time. We then removed resource and time. And so if you see here, resource roles play an important, have higher weights, attention weights. And that's what, when you remove the resource, the accuracy actually reduces. So this is how we evaluated the explanations generated by the model. we didn't get good at much. So we also looked at suffix and remaining time. Our approach worked well for next event. For suffix and remaining time, it didn't meet the benchmark. So it actually had higher MAE and even the distance measures. So to conclude, the model architectures do meet existing benchmarks when it comes to accuracy while supporting interpretability. The accuracy of the model reduced when we were looking at remaining time and suffix, and this is something we would want to look at for future work. We've also not considered the data attributes of the event. So that would be something we would need to look at, because as you have more attributes, the dimensionality would increase. And at some point, the accuracy would definitely get impacted. Finally, if you look at this approach, it's largely for a model debugging. It's still not useful for an end user maybe. And that would be the focus of our study. How do we get it generate explanations for end users? So that's all I had. Thank you.
Thank you, Renuka. Are there questions from audience?
I don't see questions in the Q&A, and no hands were raised so far.
Okay, maybe I can start. Maybe somebody.
There you go. We have a question. We have Chiara, we have a question.
Okay, good.
Marlon has a question. Go ahead, Marlon.
Yes, so thank you, Renuka, for the talk. I see that, yes, indeed, currently what you're trying to find is rather on explaining to the machine learning specialist or the data scientist what is the basis for what is the structure of the model, or the mechanisms that the model is capturing or not capturing. In that respect, though, it's kind of, interpretability is very nice, but from a business perspective, what we need is kind of more than interpretability in the field of BPM. We need actionability, which means that the model should be capable of generating predictions that will help you to do something to improve that process, for God's sake, you know. So do you have any insights into the applicability of this type of techniques that you have used, like attention layers, to tell me, you know, if I do this, my process will be better?
Yeah, thanks, Marlon, for the question. Yeah, that's right. I mean, that's a part we haven't looked at. And so the focus, as you rightly said, has largely been on saying, is this model right? Is it using the right features and so on? For actionability, whether such architectures can be used is something we'll have to, again, yeah, that's something I haven't thought through yet. That's right.
We have another question by Hans. Hans, go ahead.
Hi. Renuka, thank you for the presentation, very interesting. I must admit I have not read the paper yet. I just stumbled upon the presentation. It looked interesting to me, so maybe it's in the paper. But I was a little bit surprised to see, I mean, I understand why you do it, but I was a bit surprised to see that you used one-hot encoding and nevertheless reached the same kind of accuracies or performances as in the models you benchmarked against. Have you looked into that? Because it surprises me, because I've been doing similar things with attention and LSTM, and to me it seemed inevitable to use embedding, especially given that the vocabulary of some of the features is pretty large.
Right. So we did use embedding, but the only thing we did is we didn't reduce the dimensionality of the embedding. So if the vector was maybe having 20 dimensions, we just had the embedding vector also replicating the whole the same dimension. That's probably something that we didn't use the standard approach of not using any embedding. And yeah, and we did get the results for at least the next activity. As you may see, we couldn't meet the benchmarks for remaining time or the suffix.
Mm-hmm. Okay, so okay, that could be the reason for it.
Yeah.
Okay, thank you, Renuka.
Yeah, thank you.
Do we have other questions?
I don't see other questions in the Q&A nor from the audience directly. Chiara, you have a question? Okay.
Well, I think we can move to the next presentation. I think Andreas is going to present the next paper. Andreas, can you share your screen? So Andreas, now we move from interpretable models towards proactive predictions. And Andreas is going to present his work together with Tristan Clay and Alexander Palm, triggering proactive business process adaptations via online reinforcement learning. So, please,
Thanks a lot, Chiara. Thank you very much. Good afternoon, everybody. Happy to present this work. We did this with two PhD students of mine, Tristan and Alexander. And as Chiara already said, this is now looking a little bit beyond the prediction in order to understand whether we should really act on a prediction by doing an intervention or an adaptation of a business process. So I'll motivate the problem we're addressing in more detail and then introduce our technical solution, which is based on reinforcement learning, give you the experimental results to show that the approach is working, also compared with the state of the art, and then provide some outlooks into obvious further work. This is a very simple slide. I also show my students to explain what we mean with proactive process adaptation. So you have the process execution, which runs over time, and at a certain point you may want to do a prediction. Farbod nicely explained the predictive process monitoring approaches, and based on the prediction you may get a outcome like that there may be a violation in your process performance objectives, delay in the process, for example. And this is really the opportunity then to act on it by proactively intervening and trying to change the process, add more resources, whatever may be possible in order to bring the process execution back to normal, so that at the end of the execution, you are in a non-violation situation. This all sounds very nice, but if you look a little bit closer, there's two important requirements you have to consider. The first is rather obvious, that you should have highly accurate predictions in order to really take the right decision. And many of the work, also the previous one from Farbod we saw, is really looking at increasing the accuracy. Because obviously, if you have a false violation prediction, you do an unnecessary adaptation, which may entail costs. And if you have a false non-violation prediction, you may miss an opportunity for an adaptation, and then you may have to pay a penalty for violating your performance objectives. The more tricky thing is that if you look along the execution of the process, that obviously the earlier you can do an adaptation, the more time or more options, more alternatives you may have for an adaptation. So ideally, you want to do an adaptation as early as possible. Thing is, there's a trade-off between these two requirements, and I pulled some of the empirical data from several colleagues and ourselves, and you basically always see the same trend that at the beginning, prediction accuracy is very low, and it really increases towards the end, gets really almost perfect prediction at the end when you don't really need it anymore for adaptation because the process is over anyways, right? So at some point along this, there's a trade-off where you should really do the adaptation in the best possible way. And indeed, people have been doing that. So one of the, let's say, standard approaches in the state of the art to something you may want to call a reliability-based adaptation. You continuously generate predictions, generate some reliability indicators, for example, a class probability of random forests like Irene was doing, or we did in our previous work, a majority count of the models in an ensemble that agree on the prediction, and then you have a kind of majority vote, which gives you the probability that the prediction is correct. So you can do this, and in order to say what is sufficient reliability, you then have to set a certain threshold. Say probability of 90% for me would be sufficiently reliable, and then you act on this prediction. And by changing this threshold, you can put a lower threshold for earlier adaptations with a risk of more wrong adaptations and vice versa. Sounds very nice, and you can really do this. The downside is you don't know the optimal threshold to do so. Okay? So you somehow have to set this threshold. People have been doing this. Again, Irene and Stefan have been doing this by using a subset of the training data to really determine the optimal threshold. Downside of this approach is obviously you need a subset of this training data, but more importantly, if your environment changes over time, if you have some non-stationarity in your process environment, this is not captured anymore in your training data, and then you may have a problem that your threshold will not be optimal anymore at runtime. And this is exactly the problem we're addressing by throwing at the problem yet another machine learning approach, if you wish. And What we do actually is we say we forget about this threshold completely. So what we want to do is we just want to have the machine learn when it should trigger an adaptation, independent of whether there's a threshold involved or not. Whole idea is we combine the predictive process monitoring part, in this case from our previous work, with the online reinforcement learning agent. The online reinforcement learning agent, in very simple terms, and I have this nice little mouse diagram here, takes an action, gets a feedback for the action, and then this helps the agent to understand whether the action was the right action in the given situation, state, whatever you want to call it, right? And by doing many of these kind of trial and error interactions, the machine learns over time what would be the best course of action in a given situation to increase or maximize the rewards. In our case, we feed this online reinforcement learning part with a predicted deviation, the reliability estimate I mentioned before, and also the relative prefix length where we are in the process. And this gives the state information to the agent. And based on this information, he then determines whether to adapt or not. In the case the adaptation was a good decision, he gets a positive reward, if not a negative reward, and learns from there. Okay. Very, very simple overview. If you drill down a little bit more, you see that there's many neural networks. On the left-hand side, obviously, the typical LSTMs we use for deep learning and predictive process monitoring, but also on the right-hand side for representing the learned knowledge. The kind of reinforcement learning approach we're using is also relying on artificial neural networks to represent the knowledge, and this has certain benefits which I elaborate in a minute. Okay. As I said, we use a special form of reinforcement learning. So for people who maybe know Q-learning or SASA, this is a approach in reinforcement learning where the knowledge is represented usually explicitly in a table. And this has some shortcomings because things are represented in the table, you cannot easily generalize over unseen states. And so you have to quantize the states if you have a continuous state space like we have in the prediction case. And in our case, more importantly, in order to gain new knowledge, the machine, of course, has to try actions which the machine has not tried before, which is called exploration. And you somehow have to have a fine-tuning between how many new things you try out and how much of the old knowledge exploitation you use. In the traditional reinforcement learning algorithms, you have to fine-tune this as an engineer, as a human. In the case of this new kind of reinforcement learning approaches, you don't have to do this because action selection is stochastic due to the underlying neural network. And this has really some benefits for the non-stationarity cases we will see later. Second part of the element is, of course, you have to formulate the learning problem in a way that the machine is able to really learn what it should. And one of the key elements we realized based as a follow-up from our previous work is that rewards have to be as strong as possible. So in the case of the mouse you saw before, cheese is a very strong reward signal, right? And what people tend to do is to really model the reward based on the actual problem domain. And this may not really deliver strong reward signals. Simple example here, if you have a successful process execution, you have zero costs. And if you would use costs as a reward, you would give the machine a reward of 0, which basically is not really a strong reward signal. So what we basically did, and you find the details in the paper, we modeled really, let's say, strong signals, successful process execution, for example, a strong positive signal. Second element is you have to map the execution of a business process instance to the kind of episodes you have in your learning problem. And this means you really have to kind of wait until you give the rewards to the machine up to the very end of the process. So in this case, for example, we have different predictions, process activities. Each time the machine decides no adaptation, so it gets no reward, and only in case there is a decision or in case the execution would reach the end of the process, you would then really give back the reward. This is needed in order to really assign the rewards to the process instance and not to mix things over the execution of process instances. All right, this was very quick. I know, again, many more details in the paper, or you can have surely many questions you can ask. I pulled one example where you really show what now happens if we deploy this approach in practice for the BPIC 2017 data set. One of the interesting curves is the reward curve, which starts very badly in a negative part, but then as you see over time, it goes up and then somehow stabilizes along a relatively good level. All the ups and downs are due to the stochastic selection I mentioned before. And what you also see is that the machine somehow has learned that it's probably not a good idea to always adapt, in any situation. This is the rate of adaptations here, but somehow to find a trade-off when to adapt in order to really also have correct adaptations, so adaptations based on the right point in time to really act on the prediction. And also you can see here in the blue part that somehow there's a kind of learning of what earliness is the best in this data set. So somehow a little bit earlier the processes after some kind of ups and downs. So this is a typical things you see in reinforcement learning, which very clearly also shows the trial and error. And it takes some time, of course, until things stabilize if you start from empty knowledge at the beginning. Second example or data set is the traffic data set. This is quite nice because you see some of these bumps here. But these bumps really clearly show that the machine is able to handle non-stationarity. And if you drill down into the underlying data set, you see that the accuracy of the predictions, because we don't retrain the predictive process monitoring part, changes. So here they get better. Oh no, here they get worse because it's an error, and here they get better. And somehow the machine is able to learn that it somehow has to take different decisions because of the predictions work differently than in the previous part of the trace of the data set. Okay. A little look at the quantitative results. We used the cost models that also our other colleagues have used, which somehow has different elements. The penalty in case there's a violation at the end. We factor in the adaptation costs, but also compensation costs in the situation that you do an unnecessary adaptation, which is expressed as the fraction of the penalty costs. And then also we model the adaptation effectiveness, reflecting the fact that the later you are in the process, the lower is the probability that your adaptation will really make sense or work. This is what I mentioned at the beginning, that you basically don't have time anymore for a decent adaptation. And using this, you see here the results for the 3 data sets we used for different alphas, so for different probabilities at the very end of the process. Here it means you have a 50% chance at the end that it still works, the adaptation, and here it's a 0% chance. And the figures in general clearly show that there's an improvement over the empirical thresholding I showed as a state-of-the-art approach, really depending a little bit on the shape of this adaptation effectiveness. Very small note, the figures in the paper are smaller because in the Excel sheet we didn't summarize one of the values for kappa 4, so just if you're wondering that the figures are a little bit different, so they're actually a little bit larger than we thought. Final experiment we did is we compared with using the weak reward function we had before and the strong reward function in this paper, and using this strong reward function really helped to increase the cost savings by 36%. So very strong impact if you find the right reward function. And actually, thank you for the anonymous reviewers for pointing us to that, to do this additional experiment. It was quite insightful. All right, let me conclude. So I think we really had made the case that we can use this reinforcement learning to help the business process execution, to have an effective decision support for business process execution and management, helping to trigger what would be a good point in time to really act on a prediction. Obviously, there's several future enhancements. The first thing is we have not really differentiated between different kinds of adaptation. So we always just say adapt or not. Stefan and colleagues have done much more on that. The other thing is, at the beginning, of course, it takes some time to really learn. And for the cost comparisons we did, we basically measured the cost improvement starting from here and used the same part of the data to do the empirical thresholding as a subset of the training data. But in practice, you really want to have the machine work out of the box a little bit better. So what we're doing currently is use some pre-training using very simple synthetic business logs to kind of jumpstart this learning behavior. And the other thing is, as soon as you introduce multiple adaptation into the game, you then may also have to have a better learning strategy for exploring all these different adaptation options in order to increase the speed of convergence. And of course, final point, nobody comes around that. And I think Renuka for pointing to that. Somehow we have to explain what goes on here. And now that we not only have the supervised learning for the predictions, but also the reinforcement learning part, explanations get even more trickier because you have this sequential decision-making factor which plays into it. And with that, and thanks to my sponsors, thanks for joining and looking forward to discussions.
Thank you. Thank you. Thank you for the presentation. Do we have any questions?
Chiara, we don't have questions in the Q&A, and for now we don't have hands raised. I want to apologize. I turned off the chat accidentally for a few minutes there.
Oh, okay.
There was no issue of depriving your freedom of speech or anything.
Okay, maybe I can ask a question. I would like to know whether, I mean, you already have an idea of how you can adapt the technique in order to be able to deal also with multiple adaptation options that you want to do in the future. I mean, if you can.
I mean, this is quite natural. So the reinforcement learning algorithms can deal with multiple adaptation options. That's not a problem. So you just have to somewhat enumerate them and then also have as part of the feedback, of course, the way to understand whether this was helpful or not. It really gets tricky when you have too many of these options, which I think in the business process case could well be depending on how complex your process model is. And at a certain point, then if you have too many of these options, it means the machine takes lots of time to explore for each of the states all these different actions. And the paper I cited here is a forthcoming paper at the Conference on Service-Oriented Computing, where we did this not for business process management, but for service-oriented systems, where you have action spaces with up to 1,000 different adaptation options. And then you have to think about what is the exploration strategy you're doing. And because we can structure this adaptation space for these kinds of systems, you can also systematically explore this in a better way. Then using some of the standard machine learning approaches which are out there, here we really bring into domain knowledge or knowledge about the software system itself in order to do this better. So it's really a kind of scalability problem in the same way that reinforcement learning does not really scale if you have very large state spaces. And then we move to this policy-based kind of reinforcement learning. It also has a problem with very large action spaces. Because it's just too many things to try out at some point. So you need some clever search heuristics, to put it simply.
I see. Thank you.
Sure.
We don't have any further questions. Seems.
No.
Okay. Thanks again.
Okay. Thank you.
Thank you.
So let's move to the next speaker, who is Florian Richter from Ludwig Maximilian University in Munich, right?
Yeah.
And we are now moving towards conformance, and he is going to present his work TADE, stochastic conformance checking using temporal activity density estimation, together with other co-authors, Janina Sontheim, Ludwig Zellner, and Thomas Seid. Please, Florian.
Thank you for the introduction. Yeah, well, we are now performing a huge leap from deep learning to shallow learning. Our approach is more focused on finding a very simple but fast to evaluate model. We are giving directly a definition for the model and are not learning it. And we are focusing on the temporal aspects, and we will have a look. So everybody of you know the traditional conformance checking, the benefits and the aims of conformance checking. So can we improve something? Can we prevent some crisis events, crisis cases, and auditing for keeping the regulations on our processes? That's everything of that should be clear. And we usually take an event log, put it into a model, and then we decide if the case is all right or if we have to do some adjustments. In contrast, we are now thinking about can we somehow neglect all the structural aspects and only concentrate on time aspects? And how far can we get with that? So for example, there are some processes like not a particular disease now, but just some general diseases. They can be interpreted or represented by a Gantt chart showing all the symptoms, for example, and the ordering of one influenza towards another influenza type. The order does not really induce some differences between them. It's more like the time of when some symptoms arrive, or can there be some patient groups where they are different times for the symptoms to come active and to show themselves. So there are some processes like this also in the industrial area. There are also a lot of processes which are not really feasible for our solution. We know this, and we can discuss this later. But yeah, we are looking on the processes which are working fine for that, which have some timestamps which are well defined and so on. So let's just recap the kernel density estimation, because our approach is based on this statistic method. We show how we train a model and the parameters we are using in the model. Then we show how to score the conformance score, and afterwards we show some extension evaluations about, for our method. So just a short recap, we need kernels. A kernel is a function which is non-negative, it should be integrable, and then we are ready to go. There are a lot of kernels, and you can use very many of them with our method. We are not really focusing on a specific one, and you will see soon that it doesn't matter really much which kernel we are using here. To have this density estimation, we are adding up a lot of Gaussian kernels. So for each sample, we are looking in the data, and samples are referring to our activity occurrences in the logs. We are adding up all these occurrences or all these observations into one probability estimator, this function fh. And then we are almost done with our model. So it's a really simple method to derive a model. We just show it as with an example on actual process data. So the first step, you just left align all timestamps in the cases. So we are just looking at the time difference from beginning of a case towards the actual occurrence of an activity. So we can do this for all our training log, for all cases and all activities within these cases. And in the left bottom picture, you see all these kernels. Here we are using Gaussian kernels. You see this typical Gaussian bell curves. It's pretty much a mess here in this picture. But if we are adding up all these individual ones, we get this, this estimator on the right side, which looks more like some Poisson distribution for this particular activity, which might be the case here. There are some outliers, some peaks. These might be outliers, some delayed activities. But overall, you got for each activity in the training log such a model. And that's a simple model we can get with this method. So I told you about, we have two parameters. So first of all, we have to choose the kernel. And here you can see we are, I could also show you other pictures with other kernels. I only took here two. The Gaussian kernel with this bell curve, and the Epanechnikov kernel, which has this parabolic shape. And you see, well, there's not a lot difference between the left and the right picture regarding the kernels. The other parameter, by the way, the bandwidth, is affecting our results. So we are shifting between overfitting and underfitting here. If the bandwidth is just too small, we are highly overfitting. If we are too large and taking large kernels, large bandwidths for each kernel, then we are underfitting and have this green line. So we are looking at a good estimation in the middle. There are heuristics. I won't go into detail about this here. In the paper, we gave some examples. If you want to have a keyword, Silverman's rule of thumb is a good starting point for search in this direction. So we are ignoring the fact that we have to use any specific kernel, but for the rest, I think we are using just the Gaussian kernels here. And now the scoring. So getting any conformance score, well, we can just iterate over a case, having each activity occurring at some certain timestamp, and then we are looking up in the corresponding density estimator. What is the actual value for this? What's the probability that this activity should happen at a certain point in time? That can be done for each activity. Then we have for each case some scores. And now it's a question how to aggregate them towards one score, because usually you want to have one aggregated conformance score corresponding to, for example, token replay or alignments. There are some candidates we thought of. We could use the maximum or the minimum average, and the statistics guys would say, well, take the product because it's the most reasonable if you are talking about probabilities. Well, we can try, and we did so. We used the BPI challenge dataset from 2015. It has a lot of activities, which is fine for our method because it's very fast and very simple. It has some case lengths which are higher than the usual cases. But we can try to discover for each of these five for these five subblocks its own density estimators, and then try to classify them. So we have a classification task for our evaluation here. So we can see the maximum is not a good choice here. It's taking the highest occurrence, and this is very obvious. The maximum value would be achieved by just, in most cases, just taking the first activity. It's in the start. It has the highest probability when it's found in the beginning of a case. So this doesn't lead to any good precision here, and also not to good accuracy scoring. The minimum does make some sense. So finding the highest outlier in our case, but it's topped with the average value. So the mean here in the third section shows the best values here. Interesting part is if you compare it with the statistically more reasonable way to use the product here, the product has the problem that it actually assumes that we have case lengths of which are almost equal. So if we have cases with 10 or with 20, 30, and it differs that much, we get the problem that the product is more focusing on the shorter ones, because the products, the values which are gained by it will be just smaller, and if the case increases in length. So here in this case, you see, for example, the recall is very high for the first one. So it just pushes every case it can find into the first class, and the rest, the remaining ones are just empty or almost empty. So that's also already a little bit promising, but we can do better. So we are taking differences or time intervals from the beginning of a case to the activity occurrence. But there are some pairs of activities within cases which have a stronger correlation. And if we are using the full Cartesian product of all different intervals, we maybe can achieve higher accuracy values here. We increase, of course, the complexity, but we won't care anyways and just try it. And here, this evaluation is a little bit misleading. It was also for reviewers. We are sorry for the confusion. So we compared it here in this table with a token-based replay, but there are some problems with that. It's just comparing apple with pears. And this is clear, and we thought it would be clear to make this decision here to put it into the table, but it had the opposite effect. So of course, token-based replay and conformance checking, traditional conformance checking works in a different way. We are not looking here on the structure, and this data set, it's really hard to find with this spaghetti-like process a good way to classify it based on conformance checking here. That's all we wanted to say. It's just hard. So we can't compare with the conformance checking value. Instead, we are more focusing now on the comparison between our temporal activity density estimation and the full Cartesian version, and see that we can really increase the accuracy by finding these strong pairs of more likely activity durations between two timestamps. If we are taking a glance at the runtime, because we're promising also that we are a little bit faster, we show that we are a lot faster actually than alignments, which is obvious somehow. The token replay is also a little bit slower than the full Cartesian version, at least on this data set. Now, it's a problem that the Tate version in the last row is a bit slow. It has very small value, so it's very fast, but also has this lower accuracy. So we should keep in mind. Okay, though in the top one, we are also comparing the modeling and the scoring on both data sets, and we see that for the full Cartesian version, we need a little bit more time into constructing our models, which is fine because it's still very fast to construct them. So let's come to the end with some requirements and limitations. First of all, we need for this method a very large database. We need a lot of timestamps, but we are very fine with a lot of activities and different activities and at large cases. In general, we need a good quality of timestamps. If we don't have a good correspondence between timestamps, then the method won't work at all. We also ignore structural issues. So if two activities are occurring at the same time point, but there are some constraints in the order, we just ignore them. And we are also only considering the continuous timeline. So if we have some weekends or some batch processing of activities, our method also fails here. So in the conclusion, we have a very fast version to check for conformance checking, but in the temporal perspective. And today we also learned that the human in the loop is a really important thing, and we need also to assist the human in the loop. And by this method, we may be able to give some candidate sets of activity or of cases which are really not conformed at all. And we can maybe produce a candidate set for later order-based or structure-based conformance checking with token replay or with alignments, just by putting some step before some filtering step and helping the human in the loop a little bit. Yeah, and in future work, we maybe have some chance to build a hybrid model for conformance checking. So combining the structural and the temporal perspective, and even do it in an online way, which is more interesting for conformance checking at all. Yeah, that's it. Thank you for your attention. And I hope for questions.
Thank you.
Thank you, Florian. So I don't see questions in the Q&A. Maybe someone from the anyone from the attendees wants to raise their hand and ask. I have a question, Florian.
Yeah.
So in conformance checking, you typically have a normative model, and maybe that's something I missed in your talk. Do you have how do you represent the normative model against which you compare your KDEs per activity or per time delay between the activities?
Well, the only model we have is actually this density estimator. So we have just this very easy model where you have this timeline and can just take a look at it. The benefit for this method is also that you can just go backwards. So you have a conformance score, a temporal conformance score, and now you want to know how bad is it. So where can I have these adjustments to get it into control again, this case, for example, and then you can go backwards and find this activity which is too late or too early, for example, or which distribution is the baseline for our model. Is there some distribution which is very significant for this activity, and why do I fail with this activity?
You're looking at the same distribution, and you're trying to say, is this an outlier or not, right? You're trying to detect outliers.
Yeah.
There's no real notion of a normative model of how things should look like.
No. It's just by observation and saying, okay, that's our baseline, and now we try to find a stochastic.
We have a work where we look at distributions and we compare them against, so we do hypothesis testing and statistically compare them against the mean, median, so you might want to look into that.
Yeah.
No other questions?
We have a question from Marlon. Marlon, please go ahead.
Yes, so thanks very much, very interesting. So what I find very interesting about this is that it can be used to assess potentially to assess the accuracy of an automatically discovered simulation model, because it takes into account the stochastic temporal perspective. However, it seems to me that you somehow don't take into account, as you said, the control flow perspective at all, right?
Yeah.
And my frustration is that, you know, and I have been trying to define these measures to assess the quality of an automatically discovered simulation model across both dimensions. And what's very frustrating is that you kind of always have to end up giving a sort of relative weight to the two dimensions in a way, or giving some importance to the error in one dimension versus the other. So do you have any directions to explore to avoid defining a hybrid measure that truly treats both dimensions as being orthogonal?
Yeah, it's not that easy, right? Well, we thought about it. It's at this state. It's a more like, or it started by being a proof of concept. Can we do something only with timestamps? And then the next step would be to take into consideration the structure, so the structure of the process itself. You could, for example, just take both values, right? The traditional conformance score and our score, and just take the arithmetic mean. But that doesn't. I think that's what you also mean, that you can't really use this value because you don't know if the temporal aspects are more important for a certain process than the structural ones, right?
Yeah, yes, correct. And I could even like compute, like generate traces from the stochastic model and use a timed edit distance with maybe, or some earth movers distance to compare them to the traces in the log. But then when any notion of timed string edit distance has an inherent trade-off between the penalty given to time and the penalty given to, for example, deletion or substitution or transposition operations.
Mm-hmm. Yeah, and it's even worse. It's not only between those two dimensions, but it's also between different different activities, because different activities, like I said, there are some batched activities, there are some human performed activities, and also machine performed activities. So I think before we are processing into this direction, we need to find a way to even out all these different kinds of activities in their temporal behavior. There might be also more, and we have to weight them according to having activities which are more confident, or giving more confident scores, or giving more realistic probabilities about if the case is really not conforming or conforming at all. So it's not easy to just look on the temporal perspective, and there are some trade-offs and some thoughts which have to be made, which are not inherent in the structural perspective, I think.
I don't see
any other questions. So, well, I think we are in time. So we would like to thank you, the presenters. Arik, did you see any other questions? Sorry. We would like to thank you, all the presenters, all the people, the authors, the people who participated in the discussion, and so thanks a lot, and so enjoy the rest of the conference.
Thanks to the chairs.
Yeah, thank you.
Thank you.